Hello there, Mr. Sutton here, bringing you the IM3 solutions for Chapter 8.5, Part 2, on probability of disjoint and overlapping events. On this one, we have a box of chocolates containing 4 milk chocolates, 3 darks, and 4 white chocolates. We randomly select one, and we want to know the probability that it's a milk chocolate or a dark chocolate. Well, since we're talking about we're talking about adding probabilities, but we also have to factor into this equation whether or not there's any overlap between these two groups. Can something be a milk chocolate and a dark chocolate? Well, the way this problem is written, it looks like you're a milk chocolate, a dark chocolate, or a white chocolate. You can't be a combination of these at the same time. So this is going to be a disjoint situation. These are separate groups. We just have to add the probabilities. So probability of a milk chocolate or a dark chocolate, let's deal with each of them separately. Now, in general, the overall total number of outcomes, we have 4 plus 3 plus 4, giving us 11 chocolates. And for milk chocolates, we said 4 of those 11 were milk chocolates, so 4/11ths chance of getting a milk chocolate. For the dark chocolates, we had 3 of those, so that's a plus 3 over 11 that we have to add in there. And since there's no overlap, we don't have to subtract anything. We just add these, giving us 7 over 11. On this problem, we have a litter of kittens, and we've got 2 gray females, 2 gray males, 2 black females, and 1 black male. So that's a total of, let's see here, 2 plus 2 plus 2 plus 1 is 7 kittens. Seems about right. Let's say we randomly pick one of these cute little guys or girls, and the kitten is gray or male. What's the probability that this is the case, actually? All right, so since we're dealing with an or situation, we have to add some probabilities together. Now, is there any overlap between gray kittens and male kittens? Could you be both of those at the same time? Well, yes. In fact, there are 2 kittens right here, the 2 gray males, that are in both categories. So although we have to add these probabilities together, we want to also subtract the overlap so we're not double counting it. So since we have some overlap, let's set this situation up now. So probability of gray or male. The gray kittens, how many of those were there out of 7? 7 is our total possible outcomes again, because there's 7 overall kittens. So for grays, we have, let's see, 2 gray males, 2 gray females, so that's 4 total gray cats. And for the males, we had 2 gray males and 1 black male, so that's 3 overall, so 3/7ths that we're adding. But now we know that 2 of those grays are also males, because they said we had 2 gray males. So that's the overlap that we now have to subtract, 2 over 7. So putting this all together, we have 4 plus 3 is 7, minus 2 gives us 5/7ths. For this problem, we have a basket with 7 apples and 5 peaches. We're told 4 of the apples and 3 peaches are rotten. Ew. We randomly pick one, and we want the probability that it's fresh or it's a peach. So we need to take the probability of fresh and the probability of being a peach and add those together. But we also have to think about, is there any overlap between these groups? Are there any fresh fruits that are also peaches? Well, it looks like there are. They said there was 5 peaches and 3 of them are rotten. Well, that means that 2 of them are fresh. So some of the peaches are fresh, and that means we've got some overlap that we're going to have to subtract after we add these probabilities together. So putting this all together now, probability of fresh or peach. Overall total number of outcomes, we had 7 apples and 5 peaches. 7 plus 5 gives us 12 fruits to choose from. And the probability of being fresh, well, let's see here. This is going to take a little bit of work. They said that 4 of the 7 apples were rotten. That means 3 of them were fresh. 3 of the 5 peaches were rotten, so 2 of them are fresh. So we have 3 fresh apples, 2 fresh peaches. That's 5 fresh fruits overall. And now probability of having a peach. This one's a little bit easier because they spelled it out for us. They said we had 5 peaches, so that's another 5 over 12 that we're going to add in there. And now we have to subtract the things that are both fresh and peaches. Again, if the 3 peaches are rotten, that means 2 of them are fresh. So that's 2 over 12 we have to subtract. So 5 plus 5 is 10, minus 2 is 8, so that's 8/12ths. And then that can reduce to 2 over 3. For this problem, we have a six-sided die, and we want the probability that we roll a 1 or a 5. Since we're dealing with OR, we have to add probabilities together. And since 1 and 5 are mutually exclusive, you get one or the other. You can't get both at the same time. This is a disjoint situation, which means we just add the probabilities and don't have to worry about subtracting any overlap. So probability of 1 or 5. Overall, we have 6 numbers to choose from on this die, so that's the total number of possible outcomes. That'll be our denominator for everything here. Probability of getting a 1, that's just one of the 6 numbers, so that's 1 over 6. Probability of getting a 5 is exactly the same. 5 is also just one of the 6 numbers, so we'll add 1 over 6. And that adds up to 2 over 6, which reduces to 1/3. For this problem, we have 11 shirts in our closet. 4 are blue, 4 green, and 3 red. And we randomly select one. We want the probability that it is blue or green. Since we're talking about or gives you more, you have to add the probabilities together. And we have to think of, is there any overlap between these two groups that we have to subtract? Well, you either have a blue shirt or a green shirt, or in this case, a red shirt. There's no shirts that are multiple colors. Apparently, you have a very monochromatic wardrobe. So because there's no overlap, because we have a disjoint situation here, that means we can just find these probabilities separately and just add them together and not worry about subtracting any overlap. So probability of blue or green. First, let's talk about total number of possible outcomes. We have 11 shirts, so that's going to be our denominator for all of these fractions. And probability of a blue shirt, well, they said we had 4 blue shirts, so you have a 4 out of 11 chance of randomly picking a blue. For green shirts, you also have 4 green shirts. So we're going to add another 4 out of 11 there. And that's going to just add up to 8/11. For this situation, we have a jar containing 6 orange marbles numbered 1 to 6 and 5 green marbles numbered 1 to 5. We randomly pick a marble, and we want the probability it's orange or has a number greater than 4. So we have an OR going on, which means we have to take the individual probabilities of orange and number greater than 4 and add them together. But we also have to consider if there's any marbles that fall into both categories. Are there any orange marbles that have a number greater than 4? Well, they said here that the 6 orange marbles were numbered 1 to 6. So yeah, there's some orange marbles that are greater than 4, like 5 and 6. So because we have some overlap, that means we're going to have to subtract that after we add the probabilities together. So getting on with it here, we're looking for probability of orange or greater than 4. Let's find the overall number of total outcomes first. That'll be the denominator of our fractions. We have 6 orange marbles and 5 green marbles, and that's it. So that's a total of 11 for our denominator, total outcomes. Now the probability of just the orange marbles, they spelled that out for us. They said there were 6 orange marbles, so 6 over 11. And then for greater than 4 marbles, that's split up between the 2 different colors. So we have 6 orange marbles. Marbles number 5 and 6 orange count in this category of greater than 4. And of our 5 green marbles, we just have one of them that's greater than 4, and that's marble number 5, green 5. So 2 orange, 1 green, that's a total of 3 out of 11 that have a number that's greater than 4. Are there any that meet both categories? Well, yeah. There are 2 orange marbles that are also greater than 4, orange 5 and orange 6. So we have to subtract that 2 out of 11 marbles that are in both categories so that we're not double counting them. Because you're either counting them for the orange or for the greater than 4, not both. So putting it all together, we have 6 plus 3 is 9, minus 2 is 7, so 7 out of 11. In this situation, we have a magazine with 12 pages. We randomly open to a page. We want the probability it's page 5 or 10. So since we're dealing with OR, we have to add probabilities together. And since your page can't be both 5 and 10 at the same time, they're mutually exclusive. It's a disjoint situation. So we just add the probabilities and don't have to subtract any kind of overlap. So for probability then of a 5 or 10, first our total number of possible outcomes is going to be the number of pages in the magazine. So that's 12 for our denominator. probability of opening to page 5, it's just one of the 12 pages, so 1 over 12. The page 10 has the same probability. Again, it's just one of the 12 pages, so we're adding 1 out of 12 here. That adds up to 2/12, which we can now reduce to 1 over 6. On this problem, we have a card drawn from a standard deck. We want the probability that it is a queen or it's less than 3. Since we have an OR, we're going to be adding probabilities together. Now, is there any overlap between these groups that we have to subtract? Can a card be a queen and also less than 3 at the same time? Well, no, it can't. The cards that are less than 3, that would include the ace, if you count that as a 1, and the 2. 1, ace, and 2 are not a queen. So these are disjoint groups, and we can just add the probabilities after we come up with them separately. So probability of a queen or less than a 3. Our overall total number of possibilities, since it's just a standard deck of cards, these each have a denominator of 52. So for the queens, there's 4 of those in a deck of cards, 1 for each of the suits, so 4 out of 52 chance of getting a queen. For the less than 3s, remember that includes the aces and the 2s, and there's 4 of each of those for the 4 suits. So that's 8 out of 52 then that fall into that second category. And there's no overlap, so just adding these together, we have 12 out of 52, which reduces to 3 out of 13. On this problem, we have a standard deck of cards, and the probability of a card being red or a jack is what we're trying to find here. So since we have an OR, we have to add the probabilities of red and jack together, but we also have to wonder, are there any red cards that are also jacks that we don't want to double count? And there are. So we have an overlapping situation, and we're going to have to subtract the overlap when we get to that part of the problem. Okay, so let's come up with our probability then. Now overall, the total number of possibilities, our denominator in all these fraction probabilities, since we have a deck of cards, we're dealing with 52 cards overall. So now for the red cards, the probability of just red cards, half the cards in a deck are red. So that's 26 out of 52 that are red cards. For jacks, there are 4 jacks in a deck, 1 for each suit. So that's going to be 4 out of 52 that we're adding. But now we have to ask, are there any cards that are being double counted? Are any of these red cards also jacks that got counted twice? Well, we have the jack of diamonds. We also have the jack of hearts. Those are the 2 red jacks. So we're going to have to subtract 2 out of 52 to make that situation right. And now putting it all together, we have 26 plus 4 giving us 30. Minus 2 is 28 out of 52. And we can reduce that by 4s to give us 7 over 13. For this problem, we want to know the probability that a card from a standard deck is both a jack and a red card. This is not an or, this is an and. So total possibilities here is we have 52 cards in a deck of cards. And the cards that are both jacks and reds, let's just count them up. We have the jack of diamonds and the jack of hearts, and that's it. So that's 2 out of the 52, which we can then reduce to 1 out of 26.